Building large-scale software systems requires marshaling thousands of moving parts into a cohesive architecture. For decades, predicting the completion of these systems has been a source of significant industry risk, often resulting in projects that exceed their original schedules and budgets. Consider a standard development scenario. A project manager must plan a new build with only two initial constraints: the anticipated size of the software and a fixed delivery deadline. Armed with only the project scale and a target date, is it possible to determine the specific human effort and team size required to meet that goal? It is. This information allows managers to shift from intuition-based guessing to a process informed by historical performance data. The mathematical framework that facilitates this calculation is called the Putnam model. By establishing a mathematical relationship between the variables of a project, this model helps identify the equilibrium required to prevent the failures that occur when teams attempt to meet unrealistic deadlines. This diagram represents a closed system built on four foundational pillars. These four variables dictate the operational reality of a software project. The S stands for software size. This represents the volume of the project, typically measured in KLOC, or thousands of lines of code. The T represents time, the total calendar duration from the project's start to its completion, measured in months. The E is effort, representing the total human labor required. This is measured in person months. For example, 5 developers working for 10 months represents 50 person months of effort. Finally, the P stands for the productivity parameter. This is a metric that reflects the efficiency of the specific development environment. These four variables are mathematically linked. Within this system, changing one metric necessitates a shift in the others to maintain the project's balance. If a project is required to finish 2 months earlier, the time variable decreases. To balance the equation, the effort variable must increase, often requiring a larger team and increasing the total work required. Understanding this four-part equilibrium is a prerequisite for allocating resources effectively, ensuring the engineering team has the capacity to deliver without overextending. This formal software equation binds the step variables. S represents software size, and CK is productivity. The critical insight is in the exponents. Effort, E, carries a 1/3 exponent. Contrast this with time, T, which carries a significantly larger exponent of 4/3. This imbalance indicates that development time has a much stronger influence on the achievable software size than raw human effort. This math challenges the assumption that project duration scales linearly with team size. It suggests that doubling the number of developers will not automatically cut the development time in half. As a team grows, communication complexity increases. The overhead required to coordinate more individuals creates friction that slows the overall pace of development. The software equation provides a mathematical model for the phenomenon described by Brooks' law, that adding manpower to a late software project can actually delay it further due to coordination costs. There is an optimal schedule for every project. While stretching a timeline can lead to inefficiencies, compressing a schedule too aggressively causes the required effort to increase non-linearly. These exponents demonstrate that software development schedules cannot be managed using simple linear arithmetic. To see how environmental factors impact this math, we isolate the CK variable. Consider 2 separate software organizations. Both dedicate 10 developers to a project for 6 months. On paper, their inputs are identical. However, Company A produces 100,000 lines of code, while Company B manages only 60,000. Since the time and human effort were identical, we must look at the environmental factors to explain this 40% difference in output. Company A may use more advanced development tools, automated testing, or have a highly experienced engineering team. These factors contribute to a higher efficiency in converting work into finished code. CK is the mathematical constant that captures these environmental advantages. In the Putnam model, productivity is treated as a measurable factor that dictates how efficiently a team converts raw labor into a functioning product. We can see how this works in practice by calculating the required effort for a project with known constraints. In this scenario, software size is 120, productivity is 2, and time is 5 months. We insert these into the equation. To solve for effort, E, we isolate it by moving the variables to the other side, then cube both sides for our estimate. While professional software handles these calculations today, understanding the algebraic relationship between these variables is necessary for interpreting the model's outputs. Using this derivation allows managers to move from subjective estimates to deriving realistic, data-backed operational targets. Within software engineering, Putnam is often compared to the COCOMO model. While both are used for estimation, they serve different primary functions. Lawrence H. Putnam and Barry W. Boehm developed these frameworks to address different aspects of project management. COCOMO is primarily used for calculating the total cost and total effort required for a project based on its scale. The Putnam model is often used to map how that effort should be distributed over time, using the Rayleigh curve to plan staffing levels for different project phases. Putnam helps managers determine when to scale a team up or down, for instance, increasing staff during coding and decreasing it during testing. COCOMO provides the high-level budget and effort totals. A helpful way to distinguish them is that Putnam focuses on the relationship between people and time, while COCOMO focuses on cost and total effort. Organizations often use both models in tandem, deploying Putnam for schedule and staffing analysis and COCOMO for budgetary planning. The software equation provides a framework to map the nonlinear relationship between resources and time. Its primary value is in identifying the risks associated with compressing schedules, highlighting how effort requirements grow as timelines shrink. When developers and managers align their expectations with these mathematical relationships, they can establish schedules that better reflect the complexities of the development process. The Putnam model provides a framework that replaces intuition with a data-driven approach to planning and managing software project schedules.